Awesome. Thanks so much, y'all. Appreciate it. And thanks for being here. I'm Dan. This is John. We're going to talk today about doing deep reinforcement learning for wildland fire management. So I'm going to take the first half. John's going to take the second half. Cool. So we both work for a program called Cognitive Mission Manager in Lockheed Martin. And our goal here is to develop a suite of AI-enabled command and control tools, mostly around the use case of wildland firefighting. So what that means is we're trying to make decision support tools for the firefighters. What we want to do is either give them recommendations, what should they do either tactically or strategically, or we're trying to maybe give them like a what-if scenario type thing. Build a tool that they can try out a bunch of different approaches to fighting a fire, something like that, and then see what works, see what doesn't. This particular project that we're talking about today is trying to do what we call a course of action recommendation. And that really just means train agents in a simulation to fight a fire. If the agents start doing a good job, then you can just take the actions that the agents do and use those as recommendations. And so when we say course of action generation, we just mean if the agents do a good job at fighting the fire in the simulation, maybe they could do a good job outside of the simulation. So the way that we've tried to model this is based somewhat loosely around the actual command and control structure that the fire services use. The way they break it down is they'll have an incident, which is a fire. They'll have an incident commander who's responsible for the whole fire. And then that incident commander will divide the fire into different divisions, and they'll put a division supervisor in charge of each part of the fire. That division supervisor, underneath them, will have crew bosses. And the crew bosses are responsible for the day-to-day operations of choosing where bulldozers go, or there's a unit of guys called a hand crew, which is a bunch of people with axes, and they go and chop down trees and stuff. And so those crew bosses will dictate at the hourly level what should we actually go work on today. So we've tried to create a similar kind of framework where we have a hierarchical RL environment. We've got our division supervisors, each with a division that they're responsible for, and then we have like our crew bosses who are the actual assets that take action in the world. So that would be the bulldozers, and they would do things like drive left, or build a fire line west, or whatever, or the crew bosses, the helicopters, stuff like that. So loosely inspired by the actual command and control structure, but amenable to a reinforcement learning hierarchical approach. Okay, let me talk about our simulation. We have built a simulation that's basically just a bunch of layers of geospatial data. So we have our topography, we have our wind, the actual fire, including the heat perimeter and stuff like that. We have what we call fuel, which is basically the trees and the grasses, all the different things that might burn. Those are classified into different kinds of trees burn at different rates. It's harder to cut down other trees. So there's different classifications that you divide them into. We take all of those different layers, we stack them up, and that's our basic world. We've also developed an in-house fire propagation model. John built a lot of that. It's based on, if anybody knows the Rothermel fire spread model, and some of the other ones. We've combined a couple of models that we like, built some of our own code, and that is what's responsible for how the fire grows over the course of our simulation. We've also taken a bunch of the constants that matter for this kind of work, and we've used US Forest Service estimates to things like how fast can you drive a bulldozer up a certain level of a certain grade of land, or like how hard is it to bang through a redwood tree with a bulldozer. These are things the Forest Service estimates for us. We take those constants, we put them into our simulation, and all of that defines our environment, which we wrap up in an RLlib multi-agent env and train our agents against. So what this looks like inside of an action loop is we will have our fire, which here is red. We've divided it into, in this case, 5 divisions radially based on the center of mass of the fire. And we'll take the division supervisors, and they will act collectively to allocate the resources that they have available to them across the different divisions. So let's say they have 10 bulldozers on this particular day. The division supervisors get together and they say who should get which bulldozers. Once those bulldozers have been allocated, then each of the division supervisors takes whatever it has and it places those assets down into the world. We move down the hierarchy then to the crew boss, who are the bulldozers, and they get to decide stuff like, should I drive to the west? Should I build a fire line to the north? What should I do 5 minutes from now, 8 minutes from now, 10 minutes from now? They make their actions. We step the world, and then at the end of the day, we rotate back to the top. So that's our basic training paradigm. These we go until either the fire wins, as in it gets to the edge of the map, or until it's contained, as in it stops growing. Cool. So that's our sim. I'm going to turn it over to John to talk about some of the ways that we actually train our agents in this environment.
Cool. Thank you, Dan. So yeah, I'm going to walk back up the agent hierarchy, starting from the bottom. So the bottom level is the crew boss agents. So again, these are the ones that are responsible for actually performing the fire suppression actions. So like building fire lines or dropping water. So for these agents, the observations they receive consist primarily of local egocentric views into that geospatial data. So basically they can see around their position, what does the fire look like, what is the topography look like, what does the wind look like. And the reason this is what we give them is because like this is the information that's going to inform how the fire spreads and then also what they can do about it, so the sort of suppression dynamics. Then we also give a bit of supplemental information on the other nearby agents, which facilitates coordination. And so how do we train these agents? So we train in a cooperative multi-agent setting. So a decentralized POM-DP, if you're familiar with some of the RL stuff. And we train each agent that shares the same type with the same parameters, which makes the learning a bit more efficient. But we also give a unique agent index to each agent that allows it to take on a unique behavior if it's helpful. We also follow the centralized training, decentralized execution paradigm here. So specifically, during training time only, we use a centralized critic that can see the full state of the world. So all of the geospatial data and also complete information about each agent, and we find that to be really helpful with the training. So stepping up again to the top level here, the division supervisor. So again, the map of the fire map is divided into partitions or divisions, and each is overseen by a division supervisor. And those division supervisors really do two different actions. So first, they act collectively to decide how to allocate the available crew boss agents amongst themselves. And then secondly, once they have that allocation, they perform sort of fine-grained placement of those agents into the world. So for that first part, the allocation, because it's a collective action, we actually train them jointly as a single agent. And specifically the way we do this is, so for each division, we take the bounding box around that division, mask out all non-division pixels, and then we compress that information with a pre-trained autoencoder that sort of summarizes the important details into a division embedding. And so we train that outside of the RL process. So now we have a sort of summary for each division. We stack those on top of each other, and then we put that, so the stack represents sort of the full fire picture. Then we put that stack through a policy network that uses self-attention to attend to the relationships between these different divisions. So that allows the network to sort of see what is the relative potential for fire spread across these different divisions, which is as you can tell, is very important for deciding how to make the allocation. And so we do that with a custom RLlib RL module. And then finally, the sort of fine-grained placement is performed just by a simple heuristic. Okay, so we mentioned a few RLlib features already, but I just wanted to call out a couple more here. So we recently migrated to the new RLlib API, which actually there was just a talk about on one of the other stage. So I think it may be coming out of alpha soon, but it's been very useful for us. Specifically, it unlocked PyTorch multi-GPU training. So as you can probably imagine, these observations are very large. There's a lot of layers of geospatial data, and the dimensions are also pretty large, and especially the centralized critic, which can see the entire world. It just takes a lot of data to store this information. So training on one GPU, this severely limited our batch size, and we've found so far that with PPO, the bigger the batch size, the more stable and also the better agents perform. So being able to do multi-GPU gives us this easy lever to increase that batch size and get better agents. So we're very excited about that. We also use RayTune, which works really nicely with RLlib. So it's just a couple of additional lines of config to run our full pipeline with hyperparameter tuning on top of it. So that's been great to work with also. And I'll just talk about some of our results here so far. So because of the immense amount of potential complexity in this environment, we decided to start by building simple but still challenging synthetic scenarios to experiment with. So this has kind of let us study the training dynamics a bit and sort of figure out like how to do RL on this environment. So specifically, we've created a couple of synthetic benchmarks. So the first one, we fix all of the environmental conditions other than the wind, and we allow the wind to vary. And the second one, we fix everything except the wind, and we allow the fuel, so the vegetation data to vary in simple patterns. So far, we've achieved 82% containment on the first benchmark and 62% on the second one, and we're continuing to improve these numbers. And so the way we actually do the training here, because it's a hierarchical problem, we sort of proceed in two alternating phases. So first we train the crew bosses until they reach sort of a decent baseline performance, and then we switch, and then from that point we alternate across the level. So we'll freeze the weights of the crew bosses, train the division supervisors, and then sort of alternate back and forth. And we find that when one agent level plateaus, switching to training the other one can kind of lift the sort of collective agents out of that plateau. And so we sort of keep doing that until we reach a global plateau. Okay. And so where to next for our team? So what we're working on now is to continue to add incremental complexity to these scenarios, also add additional equipment types. So those results were just for bulldozer type agents, but there's also many other types of equipment, helicopters, et cetera. So we've been experimenting with different types like that. We're also working to continue scaling our training across larger infrastructure. And ultimately, so we've collected data for about 300 snapshots of real-world fire incidents, mostly from open government sources. And we can drive our simulation with that data. So ultimately, we'd like to sort of evaluate how well do these agents do so sort of when they're confronted with real scenarios. So thanks for coming to our talk. And if you're interested, feel free to track us down, and we're happy to talk. And just want to give special thanks to the rest of our R&D team back at Lockheed, and also to the RLlib team at Anyscale. So thank you.
Thanks so much, y'all.